My name is Elektra Wagenrath. I'm an activist in community networking and mesh networks. If you have been previously in my presentation about OLSR and beyond, you can also get that slideshow on that address that is printed here on the screen. Well, the picture for the introduction is a tower located in Bangladesh, where people share a VSAT, a satellite link to the internet, for voice over IP communication mainly. Don't get confused, this is not Wi-Fi. That giant dish is necessary in Bangladesh because the satellite link has a very long wavelength and hence the dishes must be very huge. Also, they have very bad weather conditions during tropical rainstorms, and even with a 4-meter dish, the link goes down if the rain comes too heavy. Well, why would somebody want to build a wireless infrastructure with cheap Wi-Fi devices? It's cheap, that's the first answer. It's democratic and can be used by community activists to build community networks. And of course, there are many more motivations why you could use Wi-Fi for long distance. I'll show you how it is possible. The background of the slide is a town in Bangladesh. If you look closely, you see many, many towers. That's the reason, because in developing countries, Wi-Fi is already really widespread. People are not using it for surfing on the sofa, of course. They invest lots of money and build high towers and set up long shots. So, how? Finally, the beef. The most important thing is free line of sight. And a decent and good line of sight includes a clear Fresnel zone. Don't be confused by this word. I'll introduce you to that. You need good and powerful Wi-Fi networking cards that could be switched into a non-standard 802.11 mode. Some cards, they even work in the standard modes. There are some limitation in theory in 802.11. First of all, I have to mention here the acknowledgement issue that prevents, in theory, that 802.11 link is longer than 1.2 kilometers. You need antennas with a lot of gain, and of course, directional antennas. A long shot with Omni is hardly possible because you pick up a lot of noise. What is extremely important and the source of failure for most people that try to build long shots is that they don't properly mount the antennas, especially water protect the cables and plugs. I'll give you a very, very short introduction to electromagnetic waves. If you have a conductor where current is floating through, maybe you have AC with 50 hertz. With a measure instrument, you can see that electromagnetic forces are traveling away from that wire at the speed of light. The electromagnetic waves, they consist of a magnetic force and an electric force, and they are located crosswise onto each other. The polarization could be twisted, so we could have the electric force here and the magnetic force there, or any angle in between, and some fields are even rotating while they propagate. This is the fact if you have circular polarized antennas. Well, like a water wave, you can imagine electromagnetic waves if you view the magnetic field or the electric field. I assume now the electric field as a wave where the polarity travels from 0 to negative to 0 to plus to negative over time. And these waves, these electric and magnetic forces, they travel through space at the speed of approximately 300,000 kilometers per second. And if you have a wave that changes one time per second, that means the wavelength is exactly 300,000 kilometers. So if you have a wave that changes 100 megacycles per second, the wavelength is 3 meters. And the wavelengths that we use for wireless LAN at 2.4 gigahertz are 12 centimeters long because before they pass through one complete cycle. At 5.8 gigahertz, it's approximately 6 centimeters. The most important thing if you plan to do a long shot is, like I mentioned it before, a decent line of sight. Those waves, they behave like light, so if there is an obstruction where the light cannot pass through, also your waves are blocked. With plenty of power, you may penetrate a few walls or a little forest even, but if you plan a link that should go further than a few kilometers and you don't start connecting an amplifier that is unbelievably expensive, it would not work. So nobody is going to build a link without free line of sight, only for a short distance. I had that problem recently. We did a link, it's 2 kilometers through a forest, which is in theory impossible, but we used antennas with very, very high gain, and it works, yes. But it's with very high gain, and it's not legal to do this in Germany. If you're new to the matter, what is quite hard to understand maybe is the issue of the Fresnel zone. I'll give you only a basic idea about it. There's more complexity to it. You can search Wikipedia for Huygens and refraction to learn more about it. It would be too much to tell you in a few minutes. The Fresnel zone is an area between the antennas in 3D that looks like ellipsoid. The reason for the Fresnel zone is that the waves are reflected by objects or refracted by objects that are within this Fresnel zone. This leads to waves that travel a different path than the direct path here, and that means that they travel a longer path usually. Of course, they have to travel a longer path. And this could lead to the effect that different parts of the energy that you emit on one side accumulate on the other side at your antenna that are within or out of phase. We have this dark blue wave. It travels the direct line of propagation, and this wave was reflected somewhere. It's quite strong, it had some good reflection. This could easily happen if you have metal parts in the Fresnel zone. And so it's quite strong and it's out of phase. So this energy which is going down, it subtracts from the energy that you want to receive. And it's absolutely possible, and it happens very often, that the sum of all those waves, because we're just viewing one single reflection, deletes completely the energy that you want to receive. Like I said, it's not just a single wave that gets reflected in the Fresnel zone, it's numerous waves, and yeah, they come within and without a phase. In theory, they can amplify your signal, but in practice, they won't. They just add up to a noise floor that reduces your signal to noise ratio, and therefore you cannot have a proper reception and proper data rate. The Fresnel zone is the most difficult issue to deal with if you want to do long shots. In theory, it's possible to do even with Wi-Fi long shots that exceed more than 300 kilometers. But the problem is we have an earth bulge, and the Fresnel zone is growing. So you would need infinite high towers to do this. Some people, they made an extremely long shot. There is a race for doing the absolutely longest shot. What they did, they launched a balloon and they had a 6-watt amplifier and they were able to have more than 300 kilometers. The rule of thumb is that 60% of the Fresnel zone must be kept clear of obstruction at least. It would be better to have 80% clear Fresnel zone, but 60% is the minimum. Like I said before, you need very high towers if you want to go to very long distances. So it's the most expensive problem if you want to plan or do a really long shot. In Bangladesh, we solved the problem by erecting towers of up to 35 meters. Here there is a very simple formula to calculate the radius of the Fresnel zone where it is thickest. It's 0.5 multiplied with square root of the wavelength multiplied by the distance. We do some example calculations later. Yes, well, this slide just underlines the fact that it would be nice to have at least 80% free Fresnel zone. In some cases, you can easily achieve that, but in most cases, you will be happy if you manage to have at least a 60% free Fresnel zone. It's important to consider the terrain roughness of the terrain that is between the antennas. There is a difference between a flat surface or an urban area with small houses or the center of a town with such big towers, because you have lots of metallic objects that add a lot of reflections, and these reflections, usually they won't help you, they would just reduce your signal to noise ratio. There are very complicated models to calculate this. I use a rule of thumb, and the values that I use are printed here. You can download a copy of this presentation and have this information, and of course there's a lot more resources on the web. How to deal with the Fresnel zone? As you see, if the frequency goes up, the wavelength goes down. You remember that I told you that with a frequency of 1 Hertz, 1 cycle per second, the wavelength would be 300,000 kilometers. So a link at 5.8 gigahertz has a significant smaller Fresnel zone area than a link at 2.4 gigahertz. So one measure that you can use to reduce the thickness of the Fresnel zone is to increase the transmission frequency. So move to the A band. But this is an issue. In most countries, it's illegal to use the 8-band outdoors or even use it at all. Trade-off of using a higher frequency is that you need a bigger rain margin, because waves at higher frequency are more affected and attenuated by rain and moisture. Something that helps you, antenna at the same size has 3 dB more gain at double frequency, because the reflector is bigger if you use a dish, but that's the default for long shots. The next problem that makes it necessary to have really huge towers is the earth bulge. I have these 2 blue-gray lines. That would be the mathematical line that hits the horizon and hides objects that are behind the horizon. If you would be on a boat on the water, you would see another little boat in a distance of about 12 kilometers. In fact, this mathematical line would suggest you can only see the boat about 10 kilometers far away. But there's the effect of refraction in the Earth atmosphere, and so The actual line of sight is the green line that is bent by the refraction of the humidity in the atmosphere. This refraction also happens to the electromagnetic waves, so we're quite happy to have about 20% more range that this mathematical direct line here would suggest. And I have formulas here how to calculate it. And you can calculate the earth bulge for each and every point between your antennas. Very helpful if you have a higher object nearer to one antenna that will obstruct your Fresnel zone, if you want to find out if it actually obstructs it or not. Here's a little calculation. We want to have a shot of 30 kilometers distance, and we use a frequency of 5 gigahertz. So some simple calculations. This is the more precise speed of light and speed of the waves, multiplied with the number of cycles in hertz, the wavelengths at 6 centimeters, and this will result in a Fresnel zone radius of 21.21 meters. And if we allow it to be obstructed by 30% at maximum thickness, we end up with a thickness of 12.73 meters. Pardon, it's the radius, not the complete thickness, only the radius. But it's not very likely that you have obstructions that come from the sky, of course. So the earth bulge in the middle between the towers would be 13.23 meters, which you have to add to the radius of the Fresnel zone that should be kept clear. So the minimum tower height for a 30 kilometer link on flat surface would be 26 meters. That's quite a lot. Hopefully you find too high objects like huge towers or high buildings that you can use for it. That will save you a lot of money. So finally, another physical part of the link, calculating the link. Imagine we have a transmission from this side. This is our Wi-Fi interface, which is actually transmitting. And it has an output power of plus 20 dB. That would be 100 milliwatts. The way I build long shots is I directly mount the Wi-Fi interface or the mesh router or wireless device directly near the antenna and keep the cable as short as possible. The losses that I have printed here, they add to reception and to transmission. So at the first plug connecting to your Wi-Fi card, you can assume you lose, as rule of thumb, 1 dB. If you keep the cable short, you should assume that you lose another dB. And with the next connector that goes into the antenna, you lose another dB. Well, that's not absolutely precise, and I cannot know it precise, but it's a good rule of thumb. And if you have a high-power antenna, the type of antenna that I prefer for really long shots, it's an American product from Hyperlink Technologies. I have a picture of that antenna. It has a really, really, really good gain and of 24 decibels. That is really enormous. Between the antennas, we have the propagation loss, just the attenuation that our waves experience while they travel on the distance between the antennas. And the nice thing with such a high gain antenna is it does not only amplify the transmission, it also amplifies the reception. So if you sum up all the gains and losses, in the end effect, for this example calculation, we end up with a signal strength of minus 73 dB. if you have a noise level of minus 95 dB, that's a 22 dB signal to noise ratio, and that's really good. You will have a full speed link. If you use 802.11b cards, they will operate at full speed. In fact, the links that I have built in Bangladesh, they all run at full speed. Well, transmitter power is, of course, an issue that many people think about. Of course, more is more, and more tends to be always better, but it does not really help much if you do the wrong calculation and plan a link, that has an obstructed Fresnel zone that is obstructed more than those 40% that we allow. So if you put more power into your antenna, you will experience more powerful disturbing reflections, which will eat up your signal-to-noise ratio that you want to achieve with it. So if you are lucky to be in an area like Bangladesh where there are not so many Wi-Fi links and everybody's only using directional antennas that don't spread their noise all around you, good receiver sensitivity is much more important than adding more power. Usually the measurement unit for the Wi-Fi cards is milliwatts or dBm, being 0 dBm 1 milliwatt, 2 milliwatt 3 dBm, and so on. So 3 dB more is always double of the previous value. 10 dB is the power of 10, 20 dB is the power of 100. Of course, if you start planning a link, you are looking for really decent gear, and I'm a fan of the Sinao cards with Prism chipsets. I'm a little bit outdated at the moment. Of course, there are newer cards and newer chipsets. The favorite at the moment are the Atheros chipsets, where you can use the Met Wi-Fi driver, but there are still issues with the Met Wi-Fi driver, but they work for a long shot. You can see how big the difference is between a Microsoft MN520 PCMSIA card and the top Sinao card. It's 12 dB signal difference to achieve 1 megabit. So at minus 89 dB, you will have full speed with the Sinao card, and with Microsoft MN520 would never get a ping even. I complained previously a few months ago about the quality of the Broadcom chipset that was used in the famous Linksys WRT54, but I've bought a device of WRT54 of a new series, and it's really amazing. They improved the sensitivity a lot. It became a really, really powerful device if you buy a newer hardware revision, but avoid hardware revision 5. It doesn't work with Linux. But that's a different issue.
Well, you've got the L version.
Yes, and yeah, from New Year it should be available. It is. Okay, great.
I've seen it here on the Congress.
Cool. At least it's available in Europe. It's not available in the US. Well, here is a Uber Wi-Fi card I'm dreaming of. If somebody wants to give it to me as a gift for this beautiful presentation, I would be very happy. Yeah, that's the best I could find on the market, and my favorite brand. It has enormous output power and is very sensitive, even at A. But you don't plug it in your laptop. It may ruin your mini PCI slot because it draws a lot of power. Yeah, here a little table about the free space attenuation that you have. Well, there's not much to say. If the distance is double, the attenuation will increase by approximately 6 dB. That is a rule of thumb that you can take out of the table. So at 100 kilometers distance, the free space attenuation would be 140 decibels. But use this with care. You need a decent rain margin, because once it starts raining, the free space attenuation increases, and it increases massively at 5.9 gigahertz. Yeah, little slide. So 3 dB more attenuation for 50% more distance, 6 dB more attenuation for 100 meter more distance as a rule of thumb. The margin, the link fade margin in worst case is 0.5 decibels for each kilometer if you have heavy rain or fog, and it's only 0.1 decibels per kilometer for the 2.4 gigahertz band. Of course, you should take into account that a wet antenna or an antenna that is full of snow or ice doesn't perform really well. So a radome that covers the antenna and protects it from moisture and snow and so on is really helpful, especially in this area here, if you want to have a reliable link. Well, picture of my favorite antenna. I have I'm not linked to that company, but I like their antennas and the quality is really good. It's available with a feeder. It's the same antenna for 5.8 gigahertz, and because the dish is bigger for the shorter wavelengths, it has 3 dB more gain. There are some antennas around, and even that company produces even bigger antennas, but those antennas are solid dishes. They have no ventilation and have very high wind load, and will give you a lot of headache if you try to align those antennas. Aligning these antennas, if you do a long shot, is not a trivial task. It will take you quite some time. It's like shooting with a gun and trying to hit a house in 30 kilometers distance. Well, that's a little bit exaggerated, but it should point you to the point what it actually is. If you try to move the antenna for alignment, you have to be very precise, do a rough alignment with a compass on one side and a GPS, and then go to the other side and try to align it and make really small steps. And I used Linux for doing the alignment, and Kismet, the wireless sniffer Kismet, was very helpful because it even reports broken packages. And finding a broken package is something like, yeah, hooray, at least we got something. Hopefully it's not another network. I won't say so much about cables and plugs. In fact, I really don't bother about the cable. When I was working in Bangladesh, the only cable that was available was RG213, and it was full of corrosion. And I don't really worry about it because the cable that I use is half meter long, so the half dB loss of RG213 for each meter doesn't really do much when compared with such a expensive cable that reduces the loss to 0.2 dB. It's just a marginal issue. What's more important is to use decent plugs, and for outdoor use, as far as I know, there's only one reliable type, and that's N-type. And never ever use crimp type plugs because they're not waterproof. At the place where you crimp it, it's very likely that water comes in. Unfortunately, the Bangladeshis only had those plugs, so we had to import them. As an additional measurement that you can apply, you should wrap the outer connectors with self-amalgaming tape. It's a very expensive tape that it's rubber, and after being exposed for a while, it becomes one solid tube of rubber that is really waterproof. And what we learned in Bangladesh too, it's a good thing to wrap the self-amalgaming tape again with simple polyvinyl chloride electrician tape, because the crows, they loved to pick the self-amalgaming tape. Um, the picture of that huge satellite dish where the people are working on, that was the result of the crows eating up the self-amalgaming tape. Because after a tropical rainstorm, suddenly our VSAT link was down and all the people were complaining. So let's do an example calculation for 5.8 gigahertz. I guess you already have the idea that it's my favorite band. We have the free space loss. And because we have 30 kilometers and the attenuation that additionally comes to the link if we have really heavy weather is 0.5 dB per kilometer, we have to add another fade margin of 15 dB to have a reliable link, even if it rains cats and dogs. And yeah, we assume that the terrain roughness is quite rough, so we have another loss that we have to take into account. That adds up to a total propagation loss. We have to add up 3 dB loss that we can assume being existent in cables and connectors on each side, leading to a total loss. And then we come to the good part where we have the gain of the antennas and the TX power of the Sonao devices that we used. We used 200 milliwatt cards, which is equivalent to 23 decibels. And the result is a link that even at really heavy rain conditions has minus 86.5 dB, and that provides full speed on 30 kilometers. But the effort that you have to do to achieve this is really high if you don't have high buildings, if you have obstructing objects. So it's not just buy the devices and mount it somewhere and then you have such a link. Well, of course, there are always these issues with legal limits. Of course, when I was in Bangladesh, we didn't care much about it. In Germany, maybe you should care about it. Well, if you're scared, you should. They have this stupid thing called effective radiated power. That's quite misleading, because if you have a card with 100 milliwatts, which would be the legal limit, and you apply a very high gain antenna, you're of course still transmitting with 100 milliwatts and nothing more. Well, you will hardly transmit with 100 milliwatts because you will lose 3 dB in cables and plugs, like I mentioned before. But those guys, they said, you should not be over the limit of the effective radiated power. Well, what that means is if you have an antenna that radiates like a ball to all sides, the signal, the strength of the field to all sides is the same. If you have such a dish, it concentrates all the energy to a little slot, to a little point. And because that energy is concentrated, because the antenna concentrates it, they complain about the field strength in that little field that is concentrated by the antenna. Well, I don't like it, and I think it's quite stupid. But it is there, it's the legal regulation. So you have to stay within those limits. In Germany, the limit is only 20 dB. That means an effective radiated power of 100 milliwatts. So if you have a card that has 100 milliwatts, in theory, if you have an antenna that has the slightest gain and no loss in cables and whatsoever, you would exceed this limit. You can, though, stay within legal limits and manage to do a long shot. But it will not be possible to achieve 30 kilometers, but I will show you that quite a long distance is possible even if you stay within legal limit. And the trick to achieve this is use antennas with really high gain and reduce the transmit power. As all the radio amateurs know, an antenna is the best amplifier, always, under all circumstances, because it amplifies the reception and the transmission. You cannot amplify the transmission beyond that legal limit, but you can amplify the reception and there is no legal limit for amplifying the reception. So that's what we do. We do a link with 5.8 gigahertz at 10 kilometers. That is quite amazing if you consider the high field attenuation at such high frequencies. But we have to reduce the transmit power to plus 6 dB. That's not much. We even lose 3 dB, and effectively we transmit with 3 dB on the antenna. But we have an antenna gain of 27 dB. Hopefully your antenna really achieves that gain that they promise on their data sheet. But if they do, it's possible. And you can really manage such a link and have a signal level of minus 81 dB. If the Fresnel zone is kept clear, at least 60%. And I don't have the values at the moment. Would have to switch back to that Uber card to see, but I think you should achieve at least 18 megabits per second or 24 megabits per second. Now another issue, I mentioned it already at the beginning, there are timing issues with 802.11. Here the slide is pointed to 802.11b, but the issues are the same with G or A. We have a propagation delay. Well, the speed of light is amazing fast, but if you do a long shot of 30 kilometers, it takes 100 microseconds to travel for those 30 kilometers. And for the timing of 802.11, this is a really long time. In theory, it's only possible to have 10 microseconds until the acknowledgement has to be received on the other side. But there are some things in the specs that assume collisions, that assume the negotiation of who is going to transmit next. And so some cards, they just work for long distance, and some cards, they just receive duplicated packages and get totally confused. The chipsets that I tested and that are working are the old Prism chipsets, the Orinoco chipsets, and the Atheros chipset, because there is a tool called ATH control, where you can align the timings of the acknowledgements. And so you can actually tune the Atheros chipset to a certain distance. People are working on an open source driver for Broadcom, which is a really good thing, because at the moment for the new and modern chipsets in ad hoc mode, there is the problem that the ad hoc mode is nowhere properly implemented. And I was told that the people that are working on the open source Broadcom implementation are also working on a tool that should make it possible to align the acknowledgement timings. So that would be really great. Well, if you want to do an extreme long shot, and people that did the 120 kilometer shot in Poland, I think, they used the old Orinoco chipset with only very limited power, and to overcome the timing issues that occurred at 120 kilometers, they used the old-fashioned ad hoc demo mode. And the ad hoc demo mode, it was introduced by Lucent with the Orinoco chipset, and it just doesn't send acknowledgements. It doesn't bother about acknowledgements, so there are no timing issues. You can switch this mode on at Orinoco, you can use it with host AP, and you can use it with Met Wi-Fi. So timing issues shouldn't be an issue as long as you have a free Fresnel zone and enough power, good antennas, and you didn't make anything wrong with your calculations, and have very good patience and nerves to do the proper alignment with such very narrow beaming antennas. You should be able to do very long shots. Yeah, the initial alignment I do with Kismet. Like I said before, it's possible to see even broken packages. And then we try to tune to the network that has sent us all those broken packages and optimized it until we could receive more broken packages per second until we could read the ESS ID and hooray, yes, it's our network. Yeah, it's quite nice. Okay, well, that was the presentation. You can file this document and the document about OLSR, Optimized Link State Routing Daemon and beyond, that I have shown on the second day of this Congress at this address. I would like to point you to an online link calculator, a company called connect802.com. They also have lots of documentation about Wi-Fi long shots. They're working on Wi-Fi long shots since a very long time, and it's a nice read. Okay. Questions? And use the microphone, exactly.
Okay, thank you for the talk. I have just a simple question about the use of these unlicensed frequency bands, which anyone can use. Basically, my experience with doing links, which are not long shots, which are very short links building to building, which used to work when I installed them in 2000, and which now no longer work because the Wi-Fi band in the city has become so overcrowded that there are so many transmitters all over the place that even building to building 100 meters doesn't work anymore. So okay, it is not in Bangladesh, it's in the center of Paris, so that may be the reason. But don't you think that even in Bangladesh you will reach a point where you'll have so many Wi-Fi devices all over the place producing noise that your links won't work anymore?
I would always recommend to use the A-band to build a backbone infrastructure. And a really good thing about a professional built dish antenna is it's mostly blind for interference that comes from other directions other than where you're pointing to. Of course it's an issue. As more and more people use the band, there's more and more noise, more and more reflections, interference, and so on and so on. And of course, building a Wi-Fi long shot in Paris is a hard task. I agree. In Bangladesh, the people are building towers and have directional antennas, and you must be really unlucky to be in the beam of another one. And if you're in the beam of another one, just switch the channel. And it is illegal to use the A-band, but you have lots of channels. Especially if they don't bother about regulations, which channel is allowed or not. There are a lot of frequencies that you can use with a Ateros chipset. If you don't ask any more questions, I would be really disappointed. Use a microphone, please. There's one on the stand behind you.
You mentioned using the host API driver for this loosened ad hoc mode, which doesn't use acknowledgements. The host API driver also works for Prism 2.5 and Prism 45 chipsets. Does these chipsets also support this ad hoc mode, or only Orinoco chipsets?
No. The host IP driver is for the Prism chipsets, Prism 2, 2, 5, and 3. And the Orinoco chipset is just for all these loosened cards that are around, labeled from different brands, and for the Met Wi-Fi chipset. So for older cards, there's quite some choice. And the demo mode of Orinoco and the demo mode of host AP should be compatible, but I'm not sure. I can't give you a guarantee. You're safe if you use the same chipset on both sides. Use the microphone, please.
when you said, okay, you have built some towers to mount the antennas to, and you use a very short cable to attach the RF transmitter and receiver card. So it would be unlikely to put some standard PC onto the tower because you have a short cable. Which kind of hardware have you mounted onto your towers which really works in the reliable fashion that this link can be used for production use?
Well, I can give you some recommendations. At that time, I used mesh cubes from 4G systems, but these devices are no longer available. They are now sold exclusively to a company in the US. Although the company is located in Germany, they don't sell it to us. You can use MikroTik router boards. I never used them personally, but I consider this as a very decent quality. You can have several interfaces. Of course, you can also use a PC up there, but the box is just a little bit bigger. There are the rep boards. There I can recommend you to point you to meshnode.com, I think. The people are here around in the Congress. They have very nice boxes. Looks very reliable, and you're free to put any Wi-Fi card in that you like, as long as it is mini PCI. I'm not sure it will work with that Uber card. You should ask those people if they really have plenty of power to drive such a monster. You can also use that WRT54, but I have never tried to have longer links with the WRT54 than more than 10 kilometers. People in Bangladesh did shots with 10 kilometers that work really well with the WRT54, but there may be some issues with the chipset, like I said before, the timings of the acknowledgements.
Okay, one more question. If you're not too bothered about frequency and bandwidth, and have you tried using some WiMAX equipment, or are you planning to use some WiMAX equipment instead of Wi-Fi to get potentially longer links and more robust and reliable links?
No, WiMAX was not available to me, and the central issue in Bangladesh was cost, and WiMAX is not cheap.
WiMAX base station is minimum 10,000 euros. And that's a very cheap equipment at cost from the supplier. So that's, I was asking, but.
Well, WiMAX is a different thing. I spoke to a guy from Cisco, and he told me they're quite skeptic about WiMAX. It's everybody's speaking about it, but I'm really sure if WiMAX will become increasingly popular, Wi-Fi will still be popular. It will exist in parallel, of course,
yeah,
and it will still exist for long shots because you can do it really nicely.
In theory, for WiMAX, you need licenses to use the frequencies that WiMAX is operating on. So that may not be a problem for you, but
it's.
And you have to pay for the licenses.
I'm afraid WiMAX will not be so democratic like Wi-Fi is, because Wi-Fi is just gear you buy and you can use it. With WiMAX there are legal issues.
One question about security. What about flash? If I put it on top of the roof, I think there's a possibility that the flash will crash my whole home system, everything which is connected by Ethernet, maybe.
Yes, lightning is of course an issue, and in fact one of the links that I have built in Bangladesh was destroyed by a lightning. But so was, this is of course something you have to take care about, absolutely.
So no solution until now?
No, there of course are solutions. There are resources you can find on the web about lightning protection, how it has to be done.
What do you do?
We don't have to invent it again.
What do you do if you want to have more bandwidth? I mean, 2 megs a second, that's... Some people would say that's not a lot.
Pardon?
If you want to have more bandwidth.
Oh, okay. Well, if you have only 2 megabit, you should redesign it. You can have a bigger antenna, you can have better gear, and if that doesn't help, you can just add another link. Why not mount 2 antennas? Or 3? Or 4? The tower is already existing. You just have to mount more antennas. Yeah, something I forgot to mention is when I give you the quick introduction to the polarization, if you have several antennas on one tower, it's a good thing to have some antennas horizontal polarized and some antennas vertical polarized, because then the interference is not so high, because antenna that comes with the wrong polarization is received 20 dB weaker than if it is in the correct polarization. This is also an issue if you mount such links. If you mount one antenna horizontal polarized and the other vertical polarized, don't wonder why it doesn't work. More questions? Or did I already exceed the time? No? But somebody else has to prepare, so I think we close this session now. If you have further questions, just ask. Thank you very much.